2 chapters left for the rest of the quarter. Chapter 8, which is this one, will be focusing on haloalkanes and radical reactions, so single electron transfer processes. And then in our next chapter, which is the nucleophilic substitution and elimination reactions, we'll see how fast we go. But yeah, whatever we got to finish on, let's say, the Monday after Thanksgiving will be like the majority of those material will be on your exam. What's being covered on the Wednesday guest lecture, I might touch on it, but there's a very small chance I'll focus heavily on that last guest lecture because it's unfair, right? It's a guest lecture. But nevertheless, just to keep you updated. Any other administrative questions before we move on? Yeah.
Is the final like more so on this unit or just like evenly across everything?
The final is just cumulative across the entire quarter. I don't have any preference of any topics. Maybe not so much on nomenclature, but okay. What else? Yeah, and if I did not finish chapter 9, and those chapters might also be important for your next 30B classes, I'll make sure to post the lecture note at least for you to read this through, even if we didn't got the chance to finish. I'll also see if I have time to do a recording, even if I'm not testing on it. It might be important for your 30B. Okay. All right, so let's get started on chapter 8. Right, so chapter 8 is a new class of molecules. So far, is my microphone on? Can you hear me okay in the back? Okay, sounds good. So for chapter 8, we're talking about a new class of molecules. So far, we went over alkanes, fully saturated, alkenes with double bonds, and alkynes with a triple bond. So now we're looking at a molecule, class of molecule of Rx. Right, haloalkanes. The structure is the same. We'll first go over general structure, nomenclature, physical properties on these haloalkanes. We'll briefly discuss the preparation of haloalkanes and then talk about the halogenation reaction. And at the end, we'll be talking about a reaction called radical autooxidation and addition, which is something that's common in biological systems. You've heard about like autooxidation all the time. Sounds like bad thing happen when biomolecules meet oxygen, and let's look at how that happens. All right, so getting started, haloalkanes. So these are just a quick introduction into binding haloalkanes to something we discussed. So haloalkanes or alkyl halides is a class of compound containing a halogen that covalently bind to an sp3 hybridized carbon, right? So halo stands for the halogen. Alkane specifies it is a fully saturated sp3 hybridized carbon. Normally, we write it as Rx, right? R stands for any kind of alkyl group. X stands for any kind of halogen. So halogen is fluorine, chlorine, bromine, iodine. Alternatively, we could also have a vinylic halide or haloalkene, right? So you can have a halogen binded to an sp2 hybridized carbon. So we were talking about these haloalkenes. Remember, we start from alkynes, and then you can do one halogenation to form these haloalkenes. Later on, you'll also learn molecules like haloarene, where you have a halogen binded to a arrow group. And in our lecture 8 or chapter 8, we'll be focusing on reactions of these haloalkenes. All right. Some of the things you already know, like addition of these vinylic halides based on their double bonds, then that's something you already know. But for today, for chapter 8, the new things comes from the haloalkane. So that's the structure. Then nomenclature. Right, so nomenclature, just like what we did before, these will sound like a review to you. You count the number of main chain, and you add the IUPAC name of either your bromo group or your chloro group onto your molecule. These IUPAC names build on to what we discussed before. So for example, you want to have the longer chain as long as possible, and bromo goes in front of methyl. And then in this case, chloro goes in front of your OH. And we have the stereochemistry. Trans means your chloro and the OH are on opposite faces of your molecule. And at the end, if we have a double bond, make sure you number the double bond in position number 1. So on the end, we have like 1, 2, 3, 4, 5, 6, 4 bromo cyclohexene. If you number it different way, you have 1, 2, 3, 4, 5. So we're favoring the smaller number on the bromo while keeping the other two like at the first position, keeping the alkene at the first position. And common names, I'll be right back with it. So common names, I do not expect you to know, but like very simple common names might appear. So at this moment, you should get a little bit of the idea about what my exam looks like. You might have some common name like acetylene, but nothing too crazy. Okay, question. The first one?
Yeah.
Well, the single bonds have free rotation. So we're not specify their cis or trans or RS stereo configuration, because in this molecule, we're not giving you that absolute stereo configuration. The alternative thing is if we write this as a wedge, right, and we say like, hey, there's a hydrogen that's dashed, and then you want to assign, okay, 1, 2, 3, and then assign the stereo configuration there. But without we specify whether it's wedged or dashed, you don't have information to assign the absolute stereo configuration. All right, so that's the IUPAC naming. And, well, the haloalkanes, well, generally speaking, these are important building blocks. And especially when we're talking about polyhaloalkanes, they're typically used as solvents for our organic reactions. And we've been seeing some of them, right? So the CHCl3, so these are the trichloromethane or chloroform, or the dichloromethane or the methylene chloride. Both of them are typical solvent in organic chemistry. In our previous examples, we were talking about like HCl reaction with the alkene in water solution will end up with a different product comparing to HCl reaction with alkene in these organic solvents. Because they are not they're not typically participating in our chemical reactions. And then the hydrocarbons with all hydrogens replaced with halogens are a special kind of polymers that's environmentally a problem, especially when we're looking at the per-haloalkanes, or in this case, like perfluoroalkanes, the perchloroethane, especially the perfluoroalkanes, or this one, the per and polyfluoroalkyls, because the carbon-fluorine bond is such a strong bond, people sometimes talk about these molecules as permanent chemicals because it's very hard to break down that carbon-fluorine bond and thus causing environmental problems. A little bit more information regarding the physical properties of the haloalkanes before we jump into the reactions of these alkanes. Right, so think about it. What is the more important thing? Now we're having a CX bond. So a carbon binded to a halogen. The most important property coming from this covalent bond is the polarity, right? Because of the electron negativity difference, you have a highly polar bond. Or if we write out, we have the partial positive charge on the carbon and partial negative charge on the X, and we can point the dipole moment into that direction. The dipole moment itself is affected, the strength of the dipole moment itself, or how polar that covalent bond is affected by two different factors, including electron negativity and also the bond length. Like the longer the bond length, the smaller The larger dipole moment is affected by both the charge how much the charges are separated and how much are the charges number. So in this case, we have the dipole moment might be different along the trend. So what we're saying here is despite the fact that your fluorine is the most electron negative atom, the dipole moment for your carbon Cl bond is slightly larger than your carbon fluorine bond. So in this case, we're talking about how polarizability your electron negative atom is. So even if the fluorine is more electron negative, it's not as polarizable as chlorine. But these are the things like you don't necessarily need to remember, just knowing like on top of electron negativity, polarizability, and also the distance also contribute to the overall dipole moment of your polar covalent bonds. All right. And then let's look at reactions. So the most important reaction of this part is the alkane halogenation reaction. All right, we'll first go over what is the general format of these reactions, and then we'll spend a lot of time talking about the mechanism of the alkane halogenation reaction, including how does each step take place, how to do error pushing, and then what is the rate limiting selectivity determining step, and then talking about what are the factors contribute to those observed selectivity trend, and how do we predict selectivity without doing the experiment. So lots of goals, a little bit ambitious for today. We'll see how far do we go. So the halogenation of alkanes is halogenation, we're reacting like X2 with like an R group. Right, so halogenation doesn't take place at room temperature without any light. Or the other way to put it, if you just simply mix your halogen, like Br2, and a ethane at room temperature without light, there's no reaction taking place. So somehow we need to have a trigger of this reaction for it to happen, even if the reaction releases heat. So the reason we say we only need a trigger is because once we initiate the reaction, the reaction itself is exothermic because we're forming stronger bonds by breaking the weaker Cl-Cl bond, forming the stronger carbon-Cl bond. So the reaction will release heat on itself and sustain the subsequent reaction to take place. But we do need to have some kind of initiation. And we'll go over what exactly is that initiation very soon. And also like the name here, we call this one to be a substitution reaction. It's basically one of the CH bond is being replaced by a carbon Cl bond, and the Cl-Cl bond is being replaced by a hydrogen Cl bond. And when we say substitution, we're saying a reaction in which an atom or group of atoms is replaced by another atom or group of atoms. So something you already know, just refresh your memory on that. And then the alkanes can undergo multiple halogenation, giving enough reagents, so you can form a mixture of products. So if you treat it with enough chlorine or Cl2, you'll eventually form the tetrachloromethane. But those are less important, right? So those are like observations that we know we can make haloalkanes by mixing halogens, X2, and alkanes together. And then, as chemists, we want to understand what's the mechanism and how to understand the selectivity. So I'll post these two reactions here and raise a question. Later on, we'll come back and revisit these experimental observations and see how do we rationalize these observed experimental observations. Now, what is it? Let's say we mix our propane with either Br2 or Cl2, treat it with light or heat. We can generally form different kind of product, right? You can either have a bromine added onto the center carbon of your propane or the terminal carbon of your propane with HBr as a side product. And I should probably see these should be or. All right. Alternatively, when we're looking at the when we're looking at the chlorination, we're adding the chlorine either to the internal or the terminal position, but we see the chlorination is much less selective. Both reactions favor the addition into the internal position, but the selectivity varies a lot depending on the nature of the reaction. So here I want to raise two questions that we will answer. One, how does the reaction take place? How do we write out the reaction mechanism of the halogenation reaction? Two, how do we understand the selectivity that's observed here? What are the factors contribute to the selectivity? All right, so these are my goals we're trying to achieve. So let's do the first. Let's focus on the reaction mechanism first, aka what is the reaction mechanism? All right, so this one is called a radical chain mechanism. So this will be slightly different from the mechanism you've seen before. Because in our previous example, when we're writing the reactions at different steps, sometimes we're like, oh, the protonation can take place or the addition takes place, right? So the actual rank of whichever takes place doesn't matter that much. But for the halogenation reaction, we have a specific set of reaction that's telling you, first set is initiation. We're initiating the reaction with light. And secondly, the propagation, and lastly, termination. Or in short, if we're focusing on initiation, we're talking about non-radical species are forming radical species by homolytic cleavage of a bond. Right? When we say homolytic cleavage, let's say I start from a XX bond, like a non-polar covalent bond, and homolytic cleavage would mean the electron one go to the left X, the other go to the right X. We end up generating two X dots. All right, initiation is non-radical to radical. We're cleaving a covalent bond to form radicals. In our example, we have two different kinds of chemical bond we can cleave, and in this case, the easiness to break that chemical bond is judged by its bond dissociation energy, right? So those are the things you can get by looking at a thermodynamic table. Like for example, if we're looking at a Cl cleaving reaction to form two Cl dots, and we can tell you the delta H of this homolytic cleavage reaction is about 36 kilocal per mole. Alternatively, like the breaking of a sp3 CH3 bond to form two CH3 radical, the delta H naught is about 90, very ugly, kilocal per mole. So what does it mean? It means when light is being shined into my reaction mixture, you have like the choice of breaking carbon-carbon bond, carbon-hydrogen bond, or the chlorine-chlorine bond. Or we can also write out the breaking of your carbon-carbon bond. So if we have, like, say, your propane, and you're breaking this one into, like, here and here, and you're forming like a terminal dot and H dot. So this delta H naught, let me check what is that. For this terminal, so that one is 103. Wait, 98, sorry. kilocalorie/mole, right? So in this case, what we're trying to say is, well, we're shining light onto the reaction mixture containing propane and Cl2. We're gonna break the weakest bond to form the radical initiator. So the weakest bond we have is my chlorine-chlorine bond, or your halogen bond. Yes?
Wait, for the last example, how can you do that if it's a hydrogen bond to a carbon? Do the electronegativity difference, how would it be radical?
So first of all, is your carbon-hydrogen bond a polar covalent bond? The answer is no, right? So my carbon-carbon bond or my carbon-hydrogen bond are relatively non-polar covalent bond because they have very small electronegativity differences, and hence they will also like to cleave in the homolytic fashion to form the radicals. Two, these two are not really happen. I add them here just to demonstrate that these are much stronger bond comparing to the chlorine-chlorine bond. And hence, in the initiation, more likely we're breaking the Cl-Cl bond to form the the radical initiator. All right. And before we move on, let's just quickly review on the stability of radicals because we will be needed. In our previous cases, we were discussing the allylic radical being more stable than tertiary, than secondary, than first primary, than methyl radical. And this is effectively connected to the bond dissociation energy, right? So the stronger the bond dissociation energy, the less likely we're breaking that carbon-hydrogen bond, and the more unstable we have that radical intermediate. So those are the things you can get from the thermodynamic table. We also went over this already. So first step, initiation. Generating of the radical initiator by breaking, by homolytic cleavage of a weak chlorine-chlorine bond. What about the next step? And now we have a chlorine-centered radical. What we're saying is the next step, the chain propagation, is called reaction of a reactive intermediate and a molecule to form a new reaction intermediate and a new molecule. What does that mean? So here, my reactive intermediate is my Cl dot. And here, my molecule will be my propane. All right, and depending on which hydrogen is being abstracted, my new reactive intermediate will be, well, either a secondary radical or a primary radical, depending on which hydrogen is being abstracted by the Cl dot. And my new molecule is my HCl. Or the other way to put it is if we can write out a general reaction to be like we have X dot plus A binded to B, and in here we're forming a new bond between XA and then breaking the AB bond and form another radical. So we are forming XA plus B dot. So there are two different types of propagation reaction that can potentially take place in this following this definition. The first one is your Cl dot abstracting a CH bond. So I'm just randomly writing something here, plus Cl dot, and the bonding here, one goes here, the other come and forms a bond, plus HCl. We'll talk about selectivity later on. Here I'm just randomly picking the primary hydrogen to be abstracted. And we can have a different type of the propagation, which is upon generation of this carbon-centered radical, the next step is the carbon-centered radical can react with another molecule of chlorine, right, Cl2, and form a new bond between your carbon and chlorine to form what we want as a product, and regenerating Cl dot as my catalyst. So this is what we call a propagation step, because once the initiation, we break down the Cl2 that initiate the reaction. Now you have the Cl dot around. For every reaction 1 going on, we're generating a carbon-centered radical. That carbon-centered radical will react with Cl2 to regenerate another Cl dot that can again feed in to my step 1 and continue the propagation. So that's why this is a little bit special, right? It's like a sequential way that's going in the cyclic fashion. And I'll be right with you. And in organic chemistry, typically when we're saying chain length, we're saying the number of time, the cycle of the chain propagation steps repeats in a chain reaction. Just a little bit of definition. Okay, question on chain propagation.
So is the only way to stop chain propagation to have stoichiometric ratios of all the reactants, or can you stop it in a different way?
So frankly speaking, in the actual lab, you can stop the chain propagation by quenching the reaction, saying you add something so reactive to radical that's going to capture all the active radical to something stable. All right, or very soon we'll see chain termination, which is how maybe these radicals will come together and finish the reaction. So chain propagation will just keep going until you use up everything, or you manually shut it up.
By everything all the carbons?
We're getting there. All right, so now we have the chain propagation taking place. The next question is, well, how do we stop it, right? Where does it stop? So that goes to a series of chain termination reaction. Or when we say chain termination, this is more or less the reverse of the chain initiation. Initiation starts from molecule to radical. Termination, you put 2 radicals together, you end up generating a molecule. So in this case, the chain termination, again, we're talking about radical, goes to non-radical. So this can be some kind of B dot, some kind of X dot. I'm not specifying what are these, they're just some kind of radical. They come together and form a covalent bond, BX. So how many different type of chain termination we can think about in this case? Well, so I'm just gonna list some of them that come to my mind. You can have Cl dot and Cl dot come together to form Cl2. You can have, let's say, a carbon-centered radical and a Cl dot to form the haloalkane. Note that this also forms haloalkane in some of the termination steps, but the reaction will stop there. The difference between this one is this is being a termination reaction, meaning after we form the product, there's nothing else to keep reacting. But in the previous case, we have the carbon-centered radical reacting with Cl2, so that's releasing the product at the same time forming another Cl dot. So that's a difference between propagation and termination. What else? Well, we can also have a primary radical reacting with a primary radical. So we will be generating 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6. Right, so that's a side product. That's not one of our expected products, but it can be formed. Or alternatively, if you have generated like an internal radical by abstracting of that internal CH, you can also react it with a terminal radical and form, well, 1, 2, 1, 2, 3. Right, so there are different ways of terminating the radicals. It's more like as long as 2 radical species meet each other, form that new bond, and that's called the termination of the reaction or destruction of my reactive intermediate. Yeah.
I might be wrong, but why is there an extra, why is it an ethyl and not a, or it's not an ethyl, it's like a propyl instead of an ethyl when you attach
Which one?
The bottom, most bottom one? Yeah, that one.
So we start 1, 2, 3. I'm just counting it. Is that right? 1, 2, 3. I could be wrong. 1, 2, 3, and I'm attaching here 4, 5, 6, 4, 5, 6. Yeah, it's just radical attached to the radical. Right? Radical meet each other. They form a new bond. All right. So in summary, when we're talking about the mechanism of this alkene halogenation, this is a slightly different scheme as we see before, right? So we were talking about the general reaction or the overall reaction. This one, like if we're not considering selectivity, I'm just using ethane reacting with Cl2, what do we have? We're forming a ethane chloride, ethyl chloride, plus HCl under the condition of light or heat. Right? So initiation, breaking of my weakest Cl-Cl bond, and I expect you to know how to do arrow pushing for these reactions. So for example, let's just add all the arrows to make sure they're connecting with each other. First one, homolytic cleavage, right? So 1 electron go to each side. For these single electron processes, we use this single-sided arrow. Next one, propagation. We observe I'm forming a new bond between my hydrogen and chloride. So the electron comes here, and the other electron goes onto the carbon to form the carbon-centered radical. The carbon-centered radical can react with another molecule of Cl2 to regenerate to generate the product and regenerate my Cl dot that can be involved in the propagation again. Right, so next up, we have termination, right? So we can terminate the reaction however you like, just whenever you have two radicals come together, that's called a termination step. And here too, we're forming the carbon-Cl bond. We're closing the Cl-Cl bond, and we can do it in the more exotic fashion. So this one will be the more tricky question of arrow pushing. So on the left, we see that we are forming a new bond between my hydrogen and this carbon. And on the right, this single bond got to become a double bond. So when we're doing the arrow pushing here, we'll first do this radical comes to here to bind with that, to form a bond between the hydrogen by cleaving of the carbon-hydrogen bond. And the other electron in the carbon-hydrogen bond got onto here, and the radical goes onto here. So that single bond then becomes a double bond. Now for these kind of things, it's like observing the reactant and product and know how to use the arrow pushing to direct where the electrons are going. But nevertheless, right, so for all the initiation, start from neutral molecule, go to radical. Propagation, a radical, a molecule, go to a radical, a molecule. Termination, two radical goes to two molecules. So far, so good? All right, and then let's move on, right? So remember, we have two questions. First one is, well, what is the reaction mechanism? We have that solved. Next question, what controls the regioselectivity? So going back to our reaction mechanism of what controls regioselectivity, we can go back to our mechanism and see, well, where is my regioselectivity being determined? So that's here. That's in my propagation step. Right, so upon formation of the carbon-centered radical, this one is no longer selective. But when the abstraction takes place, your Cl dot can abstract a hydrogen either from the primary position or from the secondary position to form either a primary hydrogen or a secondary hydrogen. All right, so the selectivity is being determined in this step of your Cl dot comes to abstract your hydrogen. Well, how do we explain it? Again, think about what is the factor we're trying to explain, right? So go back to our experimental observation. We have two things we wish to explain. First, it appears that abstraction of the internal hydrogen is always favored for bromination and chlorination. Why it is the case? 2, bromination and chlorination have distinct different selectivity. The bromination is way more selective comparing to the chlorination. Why it is the case? And how can we apply something we learned in bromination versus chlorination into, let's say, fluorination, and try to predict how selective that reaction is? Ready? Let's get started. Now, what are the factors? There are some things that we already know, right? So first of all, we have number of hydrogen atoms. So we're just gonna use propane as our simplistic fashion. So we have, in propane, that's the general structure. What do we have? We have 6 primary hydrogen and 2 secondary hydrogen. Or just judging by probability without thinking about chemistry, just assuming you have a Cl dot and comes try to grab a hydrogen, try to randomly break a CH bond. Now by, say, probability, there are more primary CH available than secondary CH. But obviously, probability is not the only factor, because in both cases, we see the secondary haloalkane as our major product. What else do we know? We also have stability of our radical intermediate, or thermodynamics. Right, so we went over the discussion that the methyl radical is the least stable, the tertiary radical is the most stable. Right, so, well, the secondary radical is more stable compared to my primary radical. So it appears that thermodynamics might be a very important factor in why we're observing the secondary haloalkane as our major product. And as a matter of fact, let's just calculate the delta H of the reaction together. In our previous classes, I quickly mentioned how to calculate the delta H of the reaction based on the bond dissociation energy. So let's just do that together. So in this case, what we're having is observing what are the bonds in your reactant and what are the bonds in your product. And the delta H naught of your reaction equals to the amount of energy, or delta H required to break the bond in your reactant, minus delta H of which is the energy released by formation of the bond in your product. So in this case, the bond we're breaking in my reactant is a primary CH bond. So the first one will be delta H naught needed to break my primary CH bond, which if you check the table, that's 98 kilocal per mole. Either we will give you that number or we'll give you like a table you can refer to. And plus the number of the delta H naught released in forming HCl bond, right? So this bond is the bond that's being formed, that's newly formed in this reaction. And that's going to be a negative number because we're forming the chemical bond, we're releasing energy. That's 103 kilocal per mole. All right, so the overall reaction, that's the BDE of the bond that's breaking in the reactant, minus the BDE of the bond that's being formed in your product. And we do the calculation, we end up to be 5 kilocal per mole. So the nature of this reaction is exothermic, or releases energy. All right, we can do the same for the secondary hydrogen atom abstraction. So that's delta H naught. Now we have the breaking of my secondary CH bond, which is a smaller number, plus the negative 103 kilocal per mole. So this number is the same because in both cases, we're forming the HCl, the new hydrogen chloride bond. And it's exothermic by 8 kilocal per mole. This also fits our expectation, right? It's easier to break a secondary CH bond. And what about my bromination, right? We were talking about bromination and chlorination being different. Like bromination is way more selective comparing to chlorination. And let's see what's the thermodynamics of the bromination reaction. So these are the -5, -8. We'll come back and use these numbers later on. So bromination and chlorination will do the same. We have delta H naught. This number is the same for primary CH bond, 98 kilocal per mole, minus now only 88 kilocal per mole. So the reason this one is smaller is my HBr bond is a weaker bond. Or the other way is my HBr bond has a smaller bond dissociation energy. So the formation of the HBr bond is releasing less energy comparing to the formation of the HCl bond. So taking together my boronation, my Br dot abstracting the primary CH bond is endothermic. The reaction takes energy. Right, and likewise, we can plug in the same number equals to 95 kilocal per mole minus 88 kilocal per mole, and again, endothermic. This one is 10, this one is 7. We're still relatively favoring the formation of the carbon center radical, but it's endothermic, it takes energy. And well, so far we have probability, we have thermodynamics. Both thermodynamics are predicting the secondary radical being about 3 kilocal per mole more stable comparing to the primary radical. And let's see if we can explain our radioselectivity. All right, let's try it. Let's try it out. So put it in to our experimental observation, and just roughly say like 40% primary, 60% secondary. What do we have? We have 6 primary hydrogens, and we have 2 secondary hydrogens. So if we divide that 40% by 6, we're getting something about 6.67 chance to abstract each primary hydrogen. If we do the calculation for the secondary hydrogen, we have 60% divided by 2. That's about 30% chance to abstract each secondary hydrogen. Or the other way to put it is in chlorination, each secondary hydrogen is more reactive than primary hydrogen by about, well, 30 divided by 6.67, that's 4.5 times. So you sort of fit our expectation, right? We're thinking about in chlorination, the secondary radical is more stable than the primary radical by about 3 kilocal per mole. So maybe it's only thermodynamics. So let's look at the calculation with bromination. So with bromination, then here we have again 6 primary hydrogens, 2 secondary hydrogens. We do the same kind of calculation, that's 3% divided by 6, get 0.5% for primary, and 97 divided by 2, you get about 48.5% for secondary. So that means each secondary hydrogen in bromination is more reactive than primary by, well, 48 divided by 5, 97 times. So it doesn't answer our full question, which is why bromination is more selective than your chlorination. wait, what? What else is out there, right? So far we went over probability, we went over thermodynamics. So obviously there is another factor contributing to the reaction mechanism and hence controlling the overall selectivity. I only have 5 minutes, so I'm gonna quickly introduce the concept and we'll pick up and see how that concept help us explaining the selectivity in the chlorination bromination reaction. So the factor is a kinetic factor. So remember, thermodynamics tells you relative stability of your reactant and product or relative stability of your products. Kinetics talks about how fast the reaction takes place. So faster reactions, more likely you're generating that product at a faster rate. So in this case, we're using a postulate called Hammond postulate. It is a postulate. It's generally true, but there will be exceptions, right? But for this class, it's good enough to say, like, at least for chlorination, the Hammond postulate is very explanatory. So read it. What is Hammond postulate? It's saying related species that are closer in energy are also closer in structure. Or the structure of a transition state will resemble the structure of the closest stable species. Right, so the stable species can be your reactant or, in this case, our radical intermediate. Let's say in the reaction of my propene abstracted by a Br dot. So in the actual transition state, we are expecting a partially formed carbon-hydrogen, a partially break carbon-hydrogen bond, and a partially formed, one second, let me finish this, and a partially formed hydrogen-bromine bond. So in the transition state, these two are partial bonds, right? So your hydrogen is partially leaving your carbon and partially form a bond with the bromine. So that's a transition state. And the product of this elementary transition state will be my primary radical and HBr bond. So in this statement, even if we're saying the transition state resembles the structure of the closest stable species, I say like reactant or product, like we're talking about the reactant and the product of this elementary step, not for the overall reaction. All right. And we'll pick up from here in our next lecture and say, how do we use the Hammond postulate to rationalize kinetic effect on selectivity of the halogenation reaction? And I'll see you on Wednesday.